right in some sense because
One, two,
Danish
three.
looks like this.
Okay. Okay. Hello, everybody. Last lecture. Yay! Woo! I wonder if I can finish early today. So let's see. Let's get my pen here. I want that. There we go. Okay. CS28. Last lecture. All right. So we started talking about Markov chains last time. And some of their properties. I'm going to start with a simple example that we're going to use more than once. Let's say I have a Markov chain consisting of only two states, and I define transition probabilities for these. This is P22, P12, and P21. Remember, Pij is the conditional probability that I am in state I in the previous timestamp, and I want to be in state J in the current timestamp. That's a one-step transitional probability. One of the things I want you to notice here is that this transitional probability does not depend on the time n. In other words, I could very well have written this as the conditional probability that I am in state I at time L, and at L plus 1, I am in state J. So no time dependence for Pij. In other words, I don't write Pij as a function of n. We don't write it this way. In other words, the time origin doesn't matter. You can shift the time origin whichever way you want, as long as at any time instance you are in state I, given that, the probability that you will be in state J at the next time step is given by Pij. This property has a name in Markov circles. It's called time homogeneity. You can also think of it as time invariance if you have signal processing inclinations like I do. In other words, shifting the time origin doesn't alter the nature of the system. The parameters of this chain are a couple of things. The topology, the way these states are connected together and to each other. So basically the loop and the edge structure of the directed graph. And also the values on each of those edges, which are the probabilities. Those probabilities don't change with time. All right. Last time we talked about this idea that you can. So we defined this term. So these are one-step transitional probabilities. I can also define n-step transitional probabilities. I start at state I, and I want to end up at state J after n steps. So from here to here, we have n steps. Let me erase that. And the way we wrote out the expression was that we said, okay, well, if I'm starting off in state I can get to state J in n steps in different ways. I can, in n minus 1 steps, end up at state 1, and then in 1 step jump to state j. And by our definition, this would be Rij n minus 1. And I can do the same thing by going from the ith state to the, kth state in n minus 1 steps, and then in 1 step I go to the jth state. I have a total of m states, so I can draw my diagram in this way. There we go. And P, M, J. So the transitional probability over n steps from state I to state j, we denote by this. And remember, we said this is the probability that at time n I'm in state j, given that at time 0 I'm in state I. That's our definition. And each of the intermediate n minus 1 step conditional probabilities or transition probabilities are defined in a similar way. So now, if I apply the law of total probability, I can write this as what? The sum of what? All of these different paths that I can go through to get to the jth state. So I can go, this is k. Okay. I can, in n minus 1 steps, go to state k, and then from state k, this generic state k, transition to state j. And my state, generic state k, indexes over all the m states. So this is what we have. And near the end of the lecture, we asked this question: is it possible to talk about limiting state probabilities? In other words, if I let this Markov chain start running at time 0 and I wait long enough, can I say something about the long-term probabilities of the process settling into each of these states? So suppose, for example, that I'm this orange-wearing bald dude, grumpy 50-year-old, 50-some-odd-year-old, starts at one of these states, and at every tick of the clock, I transition from one website to another. Let's say these nodes are websites. Can you say something about the probability of finding me at a particular site at some distant time in the future? So, does the Markov chain have limiting, why am I capitalizing everything? Weirdo. Have limiting state probabilities? I'm asking, actually, there are two aspects to this question. So one of them is, if I start off in state I, is there a limit? Does this exist? So that's one question. Does this exist? If it does, if it does it depend on I, the initial state? Okay? So, let's say you wait long enough and you want to assess the probability that I am visiting a particular website at some distant time in the future. can you give me a number? Can you give me a fixed number that doesn't depend on n? And if you can give me such a number, so if the limit exists, it would be of this form. Some fixed number Rij. Okay? The second question of whether the initial state matters helps us simplify the answer even more. If the initial state is irrelevant, then the limit further simplifies to what? What can I remove from this expression? Huh? The I. In fact, the more common terminology would be pi j. This is the limiting state probability for state j. That means if a Markov chain satisfies certain requirements such that there is a limiting state probabilities exist and they don't depend on the initial state. So it doesn't matter which website I start from. If you wait long enough, you can give probabilities for where I will be at some distant time in the future. Then those numbers are given by these. What can you tell me about pi 1 plus pi 2 plus pi m? It should be 1. I am going to be on one of those websites at some point long enough in the future, once the process settles. Does that mean that you can pinpoint where I am? That I'm going to be stuck in a website and I'm not going anywhere? Is that what limiting state probability mean? Let's go back to the two website example right here. Okay? So I'm visiting either website 1 or website 2. Does the assertion that there is a limiting state probability for each of these two states mean that I'm stuck in one of these two states and that I'm not moving? No. I'm still hopping around. I might be in state 1 at some point in the future and click on a link on the same website and go down the page, or follow a hyperlink to the other website and hop onto the other page. What limiting state probability says is that the likelihood that you will find me in state 1 is pi 1, and the likelihood that at any random time in the future you will find me in state 2 is pi 2. And since I can only be in one of these two states, the sum of pi 1 and pi 2 has to be 1. If we generalize that to m states, then that statement is simply what we wrote here, that the sum of all the probabilities is 1. This is a normalization equation. Now, let's look at some examples where these limiting probabilities don't exist. So, let's look at this chain. 1, 2. I think I put this example last time. So if I'm in state 1, I jump to state 2 with probability 1, and if I'm in state 2, I jump to state 1 with probability 1. Does this chain have limiting state probabilities? Why not? It's oscillatory. This chain is periodic. if I start at time 0 in state 1, there is no way you're going to find me in state 1 at any odd time instant in the future. Right? So if I'm in state 1, if x0 equals 1, then you're guaranteed that at any, let's pick any odd time, the probability that at any odd time in the future I'm in state 1, that probability is 0, and so I have to condition. We're living in a conditional space here. At time 0, I'm in state 1. At any odd time, you're not going to find me in state 1. Similarly, so this is for all k, 0, 1, 2, and so on. And the probability that you will find me in state 1, if I start in state 1, for all even times, that probability is 1. So you can see this is essentially a 2k plus 1 step transition probability. It's not converging. It keeps hopping between 0 and 1. There is no limit. So that's the first. Remember, I said we're asking essentially two questions. The answer to the first question is that there is no limit. That limit doesn't even exist, so we don't even get to go to the second question for such chains. So, periodicity in the chain ruins limiting state prospects. We're not going to harp too much on periodic chains. Detecting that a chain is periodic can get really tricky very quickly as the number of nodes in the chain increases. In general, if you can coalesce nodes in the graph such that, let's say in this case I have 3 groups of nodes, such that at every tick of the clock you have to hop from one of these groups to another, then you have periodicity. In other words, it's a multipartite graph. So the simplest one would be a bipartite graph. And identifying these is not always easy. So let's do an example here. So let's say I have this chain. 1, 2, 3, 4, 5. And is that a periodic chain? Talk to each other. Okay, Rohan. What do you want to do with this problem?
I'd say it is cyclic.
Okay. Can you classify the nodes into different groups like I did on the right? It's always, well, a lot of times it's easier in the apps. Oh, that yellow doesn't show up very well. change the color. Okay.
So I classified 1 and 5 to be
In the same group?
in the same group.
Remember, at every tick of the clock, you have to leave the group.
Okay, so I classified 1 and 5 to be in different groups.
Okay, so 1 and 5 are in different groups. I'm going to blue out the 1. So 5 is not in 1's pile. What about 2? Is that in 1's group?
It cannot be.
It cannot be. What about 3?
3 is in 1's group.
3 is in 1's group. Do we have a clustering?
Yes.
Yes. Now we have blue nodes and we have white nodes. At every tick of the clock, you go from a blue node to a white node. And at the next tick of the clock, you go back to a blue node. So this is a periodic state. And there's no limiting state behavior in this chain. All right. So like I said, I don't want to harp too much on periodic chains. The interesting stuff actually happens for chains that do have limiting state probabilities. Now the other question is, okay, so we have to make sure that the chain is not periodic. One of the easiest ways to take out periodicity and knock it out is to put a self loop on any node. The moment any node in the graph has a self loop, you're guaranteed that the graph is not periodic, or the chain. Let's go back to our two-state model. So, do I have my black? Yeah. So, but now, okay. So let's say I have. Let's draw the two-state model here. Let's say I have these two. 1, 2. They pass the ball to each other, and sometimes they hang out. And then I have a cluster of states here that do their own thing. I'm not even going to bother putting transition probabilities here. And let's say I have a single node sitting out there. So 1, 2, 3, 4, 5, 6, 7. Okay? So that's my next example. This chain has no periodicity. But, a critical arrow is missing here. But notice something weird about, not weird really. Something is happening with this chain. The middle cluster consists of nodes that, even though I might stay in there for quite some time, ultimately, what am I going to do? Ultimately, the bird is going to leave the nest. The bird who's hanging around these nodes is going to leave the nest. Either it's going to the right or to the left. This is called a transient cluster or transient class. I can write formal definitions of what transient nodes are, but I'd rather have you appeal to your own intuition. And just think in terms of what you know about directed graphs. If I start off at any of these nodes, and if you're watching me visiting these nodes, if you wait long enough, I'm at some point going to leave nodes 3, 4, 5, and 6 and end up either on the left or the right of the chain. So, a transient node is a node from which I can go. I can go to at least one other node elsewhere on the chain, but from which I can never return to where I start. So if I'm in node 3, it is possible for me to go to some node in the chain and never be able to come back to 3. That's the definition of a transient state. A cluster of these states that is maximally large, among which you can travel, but once you leave that cluster, you can't come back. That's called a transient class. A class is essentially the largest clique, if you will, of nodes in the graph that satisfy a certain property. These two clusters on the right and the left are called recurrent classes. So this is recurrent class 1. I've got 2 of them in here, and I'm going to number them. Recurrent class 2. A recurrent class of nodes is the maximally large set of nodes such that I can travel among them indefinitely. I can go from any of them and return to any of them. So once I'm in the recurrent class 1, I will always be hopping around between 1 and 2. I'm always going to be there. So that's one recurrent class. Once I go to node 7, I'm always going to be there. That class just happens to have only one node. In the original example, let's go back here. What kind of a chain am I looking at here? We know it doesn't have periodicity because it's got a self loop. Do I have a single class or more than one class? Is it recurrent, transient? Is there any transient node in this graph? Is it possible for me to leave any of these nodes and never come back to it? No. So I'm looking at a recurrent class. How many recurrent classes am I looking at? 1. It's already maximal in size. Okay. So this one is a single recurrent class chain. This one has more than one recurrent classes. If you have a chain that has more than one recurrent class, those recurrent classes must be separated by transient classes. And that's what's happening here. Okay. Now let's go back to the original question that I asked. We want to talk about limiting state probabilities. If this is the internet that I am surfing, that is the probability that you will find me at a particular node going to depend on where I start. We've already established, because we've eliminated periodicity, we know that we do have limiting state probabilities. So if you wait long enough, you can associate with me a probability of being in any of these states. What's the limiting state probability of finding me out anywhere in 3, 4, 5, or 6? 0. Because at some point I'm going to leave, I'm never going to come back. So if you wait long enough, I've left the nest. This is the nest, this chick has left. Okay? I don't come back. Once I grow my wings, leave the nest, I don't come back to this transient cluster. So the limiting state probability of finding me in state 3 or 4 or 5 or 6 is 0. But what about 1 and 2 or 7? They are not 0, but do they depend on where I started off? How does it, so tell your neighbor how the probability of finding me in node 7, for example, depends on where I started off at time 0.
You have one last home. No, I did, but now you have. So it's treated. I love how we don't show you your homework drop. quit to menu?
I don't think so.
It's okay. It's not supposed
Okay. Rohan, what do you want to do?
I'll pass to.
Pick somebody who's in a group. Was Romeo a man or a woman? That's the question. Huh? It's 2019. Yeah, that's a politically incorrect question to ask. Is Trump going to get reelected or not? That's the question. Hey, that's neutral. Agnostic.
So, if you start at...
You
7,
are?
I'm Nima.
Nima,
Yeah.
go for it.
So if you start at 7, you're for sure going to stay in 7. So it's 1.
It's 1.
probability in 7. And
So let's write that down. Probability, so the limit, as n goes to infinity, of finding me in state 7, given that I started in state 7, is 1. Mm-hmm.
And if you start in anything in recurrent class 1, you're going to stay in there as well. So, and since that's
All we need is one counterexample. So the probability that you will find me in state 7,
right,
given that I am initially
in state like 1,
in 1,
it's
is
0.
0.
'Cause
Okay?
you're gonna go out.
So the initial state matters.
Yeah. I actually had a question.
Yeah.
So we know that if we start in any of the recurring classes, we're not going to go to the other recurring class or the transient class. But does it depend where, if we were to start in the transient class, whether we would end up in the recurring class 1 or 2 with different probabilities or the same probability?
So that's a very good question. I might start off in one of the transient states, and then you want to ask the question of what's the probability that you will ultimately find me in state 1 or state 2.
Yeah, versus like 7.
Yeah. So then the algebra becomes a little more nuanced because you have to now condition on exiting the transitional class, the transient class. Conditioned on my having left the transient class, what is the probability that I will end up on the left? And what is the probability that I will end up on the right? If each of these branches has edges has probability 1/2, then I'm equally likely to go to one of the two sides. If they are lopsided, then I'm likelier to go to the side that has the higher probability. So you're going to have to apply the law of total probability to figure that out. So now we're getting this intuition that if I have more than one recurrent class, so again, we eliminate periodicity. We're not dealing with a periodic chain. If I have more than one recurrent class, the limiting state probabilities depend on where I start off. And if I don't have more than one recurrent class, the limiting state probabilities don't depend on where I start off. So, so going back, so if we have only a single recurrent class, the Rijns, which are defined as the probability of finding me in state J, given that at time 0, I'm in state I. These reach a limit that only depends on the last state. Yeah. You gotta get the mic, Rohan. I can't hear you.
Going back to the example above, when you said like the probabilities of entering, if they're lopsided, then the probabilities of like the steady state probabilities of being in either recurrent class conditioned on exiting would be different. But if they were, is it possible to construct a case where those are the same, but the probabilities within the transient class are different enough that the recurrent class final probabilities would also be different?
So, to deal with the limiting state probabilities for this chain,
Yeah.
all you have to do is consider the left chain separately in its own right and the right chain separately in its own right.
Okay.
That's all you have to do. So it's as if I want to find the limiting state probabilities of the left chain, I will just chop that off and deal with the limiting state probabilities there. And I will chop this off and deal with the limiting state probabilities there. That's a little bit of a detour from what we're doing. We can talk after class if you want. Notice what's happening here. I have a conditional probability law. And as n goes to infinity, I'm saying not only that the n doesn't, the initial, not only that I have a limit, but that the initial state doesn't matter. So what this means is that the state at time n becomes asymptotically independent of the state at time 0. In other words, the chain erases any memory of where you started off with as time goes forward. So let's see what that means. If I want to figure out the unconditional probability that at some time n I am in state j, one way I can write that out using law of total probability, going back to the very first lecture or two in our probability module, I can do that by summing over the joint probability of being in state j at time n and being at state I at time 0. Do you agree with this? At time 0, I'm in one of the m states. So I can write the probability of the event that I'm in state j at time n as a sum of these joints. And then, according to conditional probability formulas, how else can I write this so that I get this guy in the equation? Can you give me an expression involving conditionals? xn equals j, given x0 equals I, px0 equals I. I start off in some state I, and so the joint is the product of this conditional and the a priori probability that I'm in state I. So that's my expression. And this, of course, is simply Rij at n. Is it not? Isn't that how we defined it? The transitional probabilities? Yes? Okay, good. Now I'm going to take limits on both sides. And I'm going to shamelessly move the limit inside the finite sum. And this px0 equals I has no dependence on n, so it doesn't really matter. So I have this blob here, and I've got this blob out there. Okay. The left-hand side is the answer to the question, what is the likelihood that you will find me in state J if you wait long enough? Isn't that what that left side is? If you wait long enough, that's where n goes to infinity comes in. You wait long enough. What's the probability that you will find me visiting website J? Okay? Now, we said that if we have a single recurrent class, this limit exists, and it doesn't depend on the initial state. So I can simply replace that with my pi j. It's some number, only depends on the state j, because the limiting state exists. And I have p x 0 equals I. Pi j has no I in it, right? So I can pull it out of the sum. Pi j. And my sum now goes from 1 to m. P x 0 equals I. What can you tell me about this sum? It's 1. I'm initially in one of those m states. So this is 1. Oh, this has to be pi j, sorry. So that means the probability that you find me in state j is that pi j to which these n-step probabilities converge to. There you go. Now, I want to look at these probabilities in a slightly different way. I am interested in finding myself in state J. In the prior step, I'm either in state J or in, I'm sorry, actually I don't need this. In the prior step, I'm in one of the M states. And if I'm in state 1 in the step prior, there's a probability, P1J, that I will transition to J. There is a probability, PKJ, that I will transition to J. There is a probability, PMJ, that I will transition to J. These are all the different ways I can end up at J at any given time, whether I'm taking limits or not. The probability that I'm in state 1, if I wait long enough, is pi 1. The probability that I'm in state K is pi K. The probability that I'm in state M is pi M. Can you give me an equation for pi j based on all these probabilities that I've labeled on the diagram? Yeah. There are two things that throughout this lecture and the Markov discussion are your friends. The law of total probability and soon enough, the law of total expectation. Everything we talk about practically has to do with these two rules. Whether you apply these rules in an unconditional space or a conditional space, that's a separate question. But we are only applying the law of total probability in most of what we're talking about. So the probability of finding myself in state J is the probability that in the prior step I was in state 1, and then I transitioned from 1 to J, plus the probability that I was in any of these other states, let's say the generic kth state, times the probability that I transition from K to J, and all the way to probability that I'm in the mth state times the conditional transitional one-step transitional probability. So pi j is the sum of all these probabilities. Pi k, times p k j. And this I can write for all the states. So I've got m equations, m unknowns. I'm interested in solving for these probabilities, right? I want you to find what the probabilities are of you finding me in any of these m websites, if you wait long enough. M equations and m unknowns. Well, sounds good. You took 16A, they probably told you that's good. Am I off the hook? Turns out the answer is no. These M equations are not independent. If you notice, I can use the value 0 for all of the probabilities and it would satisfy these equations. If all the pi i's or pi k's are 0, I satisfy these inequalities. What's that additional piece I need? So it turns out m minus one of these equations are independent. It's just that last one depends on the other ones. What else do I need to be able to solve this? The sum of all of them is 1. That's what I need. I need the normalization. So these are the balance equations. That's what they refer to, balance equations. And this is the normalization equation. Okay? So the combination of m minus 1 of the top set of the balance equations and the normalization equation can be solved for each of the probabilities, and we get the limiting state probabilities. Let's do this for the two-state problem. So I have two states. So this is an example. I have two states. Where are my numbers? Here we go. So P11 is 0.5. P22 is 0.8. P12 is 0.5. And P21 is 0.2. Okay? Let's put a little spin on this, huh? Rohan is my guinea pig here. This note corresponds to Rohan being up to date with CS70. And this is Rohan behind. Did I just hear you say, Rohan, that these probabilities make sense in your case? Rohan behind the game. Okay? So what's the probability that if you wait long enough weeks in the semester, or long enough days, Rohan will be up to date, and Rohan will be woefully in trouble? Alright, let's see what we can find. So, what are the equations that we can write? Can you help me with the balance equations? Help me with pi 1. Pi 1 is what? There are only two nodes, so we've got two equations, two unknowns. One of those two equations says the same thing as the other one, and we'll bring in the normalization equation to help us solve it. So let's just write the normalization equation first. Pi 1 plus pi 2 equals 1. What's the other equation? What is pi 1? Can you tell me? Based on what we just wrote up here. Here. Use this to help you out. Give me the symbols and then we'll plug in the numbers. So, I might be in pi 1 and then transition back to 1. Or Rohan might be up to date, and the next time instant or next week, whatever your time scale is, he will be up to date. Or, at the previous instant, he may have been behind and but manages somehow, miraculously transitions to the state of being up to date. He catches up with the material. All right, so we've got two equations and two unknowns. Pi 1 plus pi 2 is equal to 1. And here I have pi 1 equals, what's P11? 0.5. Pi 1 plus P21. P21 is 0.2 times pi 2. Can you all solve this set of two equations and two unknowns and tell me that if you wait long enough in the semester, are you likelier to find Rohan all caught up or behind?
Behind.
By inspection.
Was that Rohan answering? That was Rohan's so-called friend answering. Okay, give me numbers, folks. Actually, give me symbols if you can, give me numbers. And then I'll give you the symbols, which you can play with later. What's pi 1? 2 over 7. Which makes pi 2 5 over 7.
That's not bad. This is a 28% chance I'll pass this
And
class.
symbolically, if you wanted to solve it, you'd get these expressions. I'll skip over the details of
I'll
those.
just be up to date with my failures.
So, given the probability structure of this problem, we are likelier to find Rohan behind schedule than all caught up. And you can also guess that, by the way, from the probability values that we put on the notes. You're dying to say something. What is it?
You could also guess that just by looking at Rohan without even the graph at all.
Yeah, so by looking at the graph, notice the state of being behind is a stickier state. You're likelier to go from that state back to that state. There's an 80% chance that Rohan will remain in the hopeless state of being behind.
It's not
And
hopeless.
whereas, on the other hand, when he's in the caught up state, it's a coin flip. The following week, he might be equally likely to stay caught up or to fall behind. So from just the probability values on this, you should be able to guess that the limiting state probabilities are lopsided, and that's what happened. Okay? All right. Now, let me go to a few other concepts. So I'm done with that, done with that, done with that. Yay! Oh, I like putting these tasks away. Now, in the remaining time that we have, I'm hoping I can talk about 4 topics that are closely related. Absorption probabilities. If I don't get to all of them, I don't get to all of them. Too bad. Mean time to absorption. Mean first passage time. And mean recurrence time. I'll probably sacrifice mean recurrence time. Okay. So, what is absorption? Let's say I have a bunch of recurrent states. Let's give them numbers, 1, 2, 3, and then let's say I go to the state 4, and The numbers here don't really matter. 0.5. Let's keep 0.6, 0.8. By the way, I hope you noticed that the outgoing probabilities from every node must add up to what? 1. Thank you. Oh, awesome. And so, let's see. I wanted this to go this way, this to go this way. So what's the probability on this branch? Right here. Do you see it? Yeah. 0.4, because 0.6 of it is going to 2. 0.4 has to go up. And then this one? 0.5. All right. Notice we have a state. I don't know if you were here early on in the semester when I was sitting in the audience and Satish was talking about graphs. This state here is a greedy state. It takes, doesn't give. I like to call it a roach motel. Roaches check in, but they never check out. Roach motel. So this is an absorbing state. So if I end up on that website, I've fallen into 4 and I can't get out. That's how it is. Okay. Now we want to figure out what the expected number of transitions mu j is, or mu I, until we reach, or we check into the roach motel, or the absorbing state. So mu I is my initial state. If I'm in state I, how many transitions or steps on average I have to take, the chain has to take before the roach finally checks into the roach motel? Okay. What do you think? I'm in state I. From state I can go to any of the states, including I itself. Right? So I can go to 1, to some intermediate state J or M. By however number of steps, right? And some of these branches may have 0 probability. So I have PI1, PIJ, PIM. If I end up from state I to state 1, what is the expected number of transitions that I'm taking? So it'll be 1 step going from I to 1 plus mu 1 by definition, right? Mu 1 is the expected number of checking into the roach motel if I'm at state 1. And similarly here I have 1 plus mu j, and here I have 1 plus mu m. So can you tell me then what mu I is? How would I write this out? This is a probability tree. And we're living in a conditional universe, but that doesn't change the fact that I can use law of total probability of law of total expectation to solve my problem. Everything is conditioned on my being in state I. and I'm trying to figure out what the expected number of steps is to get to the absorbing state. So this is actually a conditional expected value, this mu I. The conditioning event is that I'm starting off in state I. So how do I write this out? It's got to be a sum of something, right? What is it a sum of? Sum over what? All the steps, all the states. And then what's the kernel of this sum? 1 plus mu j times. So notice, you can think of this as a random variable, each of these outcomes as a random variable. And so if I go through the top path, that's the value I'm going to take. If I go through this jth path, that's the value I'm going to take. So I'm essentially taking the expected value. So each of these, the jth path happens with probability P what? Pij. And now I have summation j from 1 to m. I'm going to break this into two sums. Pij plus sum j from 1 to m Pij times mu j. What can you tell me about this first sum? It's 1. If I'm starting off in state I, at the next step, I'm going to end up in one of those m states. So this is 1. And this is the second term that remains. And I have my mu I. And this is true for I equals 1, 2, through m. Thankfully, we don't run into the same problem as the limiting state probabilities. So I have a system of m equations and m unknowns, and these are fortunately the equations are independent, so I can solve this system to find the magical numbers, the expected number of steps it takes for me to get to the absorbing state. Yeah. So an absorbing state or class is a set of states that once you, so let's say I'm talking about an absorbing state. I go into that absorbing state and I'm stuck there. So absorbing states are recurrent. If I have a class of them, that means I have a blob of these nodes. Once I enter that cluster, I can never get out of that cluster. Just like the example we had early on up here. So each of this cluster is an absorbing cluster, this cluster is an absorbing cluster. Once you enter them, you're stuck there. So the question we're answering here is actually not that I'm entering a particular absorbing state. It's the expected time to absorption. So if I have a cluster of absorbing states, I can think of that whole thing as a supernode and answer the question of what happens, how many steps does it take for me to enter that supernode? Okay? All right. What was the next topic I wanted to talk about? So that was mean time to absorption. And let's talk about mean first passage time. They all play on the same concept of law of total expectation. So suppose I have a chain like this, 1, 2, and some state I'm going to label as S. Let's say I have arrow here, arrow here, arrow here, an arrow there, and some bidirectional arrow here. So this is, I'm going to restrict this to single recurrent classes. So suppose I'm looking at a chain that has a single recurrent class. I'm interested in the mean first passage time to state S. Let me write that in a slightly different way. Given that I am in state I initially, given, what is the expected number of steps such that at time n I end up in state S, so such that for the first time. I call that Ti. I'm going to go over that again with a different color. Given that I start off in state I, what is the expected number of steps it takes for me to end up at state S for the first time? Whatever that number is, I'm going to call it Ti because I'm conditioning on the initial state being I. That's what I'm after. Okay. Well, let's draw the diagram again. I'm in state I. From state I can go to... So why is it that I'm starting n greater than or equal to 0? If my initial state is S, I'm already home. It's like those billboards. If you were here, you'd be home now. If I'm already in state S, I'm done. 0 steps. But if I'm in any of the other steps, it would take a positive number of transitions. Okay. So, first of all, I want you to realize that I can simplify this diagram, this Markov chain here, by removing all the outgoing nodes from S. Why? Because I'm only interested in the first time I get to S. What happens after I get to S for the first time? I don't know and I don't care. E-I-E-I-O. So simplify the graph. S, 2. So I might start with state 1. I'll go to S. And if I go to S, for all I care, it can be a Roach Motel. I don't care what happens afterwards. What matters to me is how long it takes me to get to S for the first time. Okay. So, we have, just like before, these M possibilities. I can go from state I to state 1 with probability Pi1. I can go to state J with probability Pij. And I can go to state M with probability Pim. And if I go to step 1, then what's the... so first of all, let's make one thing clear. S is 0. If I'm already in state S, the expected number of steps is 0, conditioned on that initial state. Now, if I go to state 1, what value am I looking at? How many steps? How many expected steps? One plus T1. It's just like before. 1 plus Tj. And 1 plus Tm. Okay? Now, so now I'm interested in Ti. So that's simply the sum over all j intermediate states of 1 plus Tj, if I end up in this generic state j as an intermediate step, times Pij. And for the same reason that we got the formula above, we're going to get 1 plus the summation from j equals 1 to m Pij times Tj. Tj. There we go. Again, we have m equations in m unknowns. I'm going to skip that last part and instead do an example that I like that makes use of this and the absorption time. Suppose, so this is an application. I think we can make pretty good progress with it. I am looking to find a particular bit string. Let's call it a code word, a binary string, in a bit stream. So I start parsing a bit stream in search of a particular bit string. What is the expected number of trials? Number of trials or bits, trials or bits parsed until, and that means up to and including, the appearance of a given binary string. How is that a Markov chain? So let's say the bits are 1 and 0, the ith bit, with probability p and 1 minus p. Okay, Bernoulli. They're IID. Let's just make that assumption for now. And let's say I'm after the code word 1, 0. I'm going to parse my bit stream until I see a 1, 0 in that sequence. Actually, let's make it more interesting. I've got to give you something to do at home. Let's look for this string. Okay? So your friend has sent you a secret message. If the stream contains 110, you're going to go and dunk your head in a bucket of ice. Now, how do I map this to a Markov chain? Well, how many states could I possibly have? If you think about each state as being the number of matches to the string. I can have how many matches? 0. Three. How many states is that? No, I don't have 4. No, wait. So, I can have a maximum of, I can have anywhere between 0 and 3 matches. How many states is that? 4. I'm going to label those states by numbers. 0 matches, 1 match, 2 matches, and 3 matches. So when I have a 3 match, that means I found my sequence. When I have 2 matches, that means I'm here. When I've had 1 match, that means I'm here. And when I have 0 matches, it means I have 0 matches. Now, how do I draw the transition diagrams for this thing? Let's say initially I'm sitting on a bit that is 0. What can possibly happen? The next bit might be 0 again, with probability 1 minus p. Or the next p might be a 1, in which case I go where? To 1, because I have my first match. And the next bit after that might be another 1, which happens with probability. I might have I might get a 0, in which case I go where? Back to square 0. And that happens with probability 1 minus p. And and if I get a 1, what happens? I go to 2, because now I have a double 1. Right? And that happens with probability p. So there's no self loop on 1. Once I come across the first bit 1, one of two things can happen. The next one can be 0, in which case I'm back to where I started. Or I get another 1, in which case I've got 2 matches. Now, once I have my 2 matches, the next bit could be a 1 or a 0. If it's a 0, what happens? I go where? Everybody. If I get a 0 after these 2 1s, where do I go? 3. I'm done. I mark it as success. And that happens with probability 1 minus p. And if I get another 1, where do I go? I have 2 1s. I get another 1. I stay here because the last 2 bits are 2 1s. And once I'm at 3, I can just label that with a 1. Okay? So now the expected number of steps to get to a perfect match will be a computation involving T0, T1, T2, and T3. So you've got 4 equations, 4 unknowns, and you can figure out the numbers. Okay? I like this example a lot because it also gives you a practice of how looking at a problem that you never would have thought was even a Markov chain problem, and you're converting it and modeling it with a Markov chain. It's a very powerful tool. It has been an absolute pleasure being with you folks this semester. Thank you. Thank you. I wish you all the best on the final. I will try to tame the final as much as I can. No guarantees when working with Satish. Yeah, let me pack first.